Hi students, welcome to Yash Academy YouTube channel. Today in this video I am going to discuss the most important point, that is how to determine the geometry of any molecule or ion. First you have to analyze Levy structure, that is the electron pair arrangement in given molecule or ion, and then you have to analyze the molecular shape, that is the geometry, which is based on the valence shell electron pair repulsion theory. Means this is particularly related to valence shell electrons. So you should know the valence electrons of each central atom in a given molecule or as a total molecule. For example, you take the elements beryllium, carbon, nitrogen, oxygen, iodine and xenon. Their atomic numbers 4, 6, 7, 8, 53, 54 respectively. So you write valence electrons. In beryllium there are 2 valence electrons, in carbon there are 4 valence electrons, in nitrogen 5 valence electrons, in oxygen 6 valence electrons, in iodine there are 7 valence electrons, and in case of xenon there are 8 valence electrons. For example, you take beryllium chloride. Beryllium chloride. So this is the beryllium chloride structure. Now count the number of valence electrons in each. Beryllium there are 2 valence electrons, and in case of Cl there are 7 valence electrons, there are 2 Cl atoms, so there are total 16 valence electrons. Correct. So the influence of electrons of beryllium is particularly in 2 regions, 1 and 2. There is no any lone pair of electron on beryllium atom, so we can say that there are 2 regions of electron density. So this molecule has a linear geometry with bond angle 180 degree. This molecule has a linear geometry. Or you take example of carbon, that is the carbon dioxide. Carbon dioxide, write the structure of carbon dioxide. Carbon 4 valence electrons, plus there are 2 oxygen atoms, each having 6 electrons, valence electrons. So 2 into 6, 12 plus 4, 16 valence electrons. So carbon is the central atom, so there is no any lone pair on carbon atom. So the influence of electrons of carbon in only 2 regions or 2 domains. So 2 regions of electron density, and so this molecule has linear geometry with bond angle 180 degree. Now we take example of nitrogen, NO2 minus, that is nitrite ion. So nitrogen 5 valence electrons. There are 2 oxygen atoms, each having 6 valence electrons, but it has 1 negative charge, so it accepts 1 electron. So total electrons 12 plus 5, 17 plus 1, 18 valence electrons in case of NO2 minus ions. So you can write like this. And nitrogen has a lone pair of electron and negative charge NO2 minus ion. So nitrogen electron domain region or electron region is 1, 2, 3. So there are 3 regions of electron density. So we can say that it has a electron geometry trigonal planar. But actual geometry of this molecule is a bent shaped. Why? Because there is a presence of lone pair of electron on nitrogen. So there is a decrease in the bond angle. So it has a bent shaped geometry. Now oxygen, you take example OF2. Oxygen difluoride, OF2. Now oxygen is a central atom in this molecule. It has 6 valence electrons, but out of 6 valence electrons it uses only 2 electrons. So there are 2 lone pairs. So total electron region is a 1, 2, 3, 4. So it has a 4 regions of electron density. So it has a electron geometry tetrahedral. Electron geometry is a tetrahedral, but actually this molecule has a bent or V-shaped due to presence of 2 lone pairs on oxygen atom. So molecular geometry of PeCl2 is linear. Molecular geometry of CO2 is a linear. Molecular geometry of NO2 minus ion is a bent shape, and molecular geometry of OF2 molecule is a V-shaped or bent shaped. For example, you take next example, that is iodine I3 minus ion, triiodide ion. Triiodide ion, there are 3 iodine, each contain 7 valence electrons. 1 electron is accepted, so 22 valence electrons. So you can write like this. Minus 1 pair, second pair, third pair, and 1, 2, 3, 1, 2, 3. So this iodine, central iodine, has a 2 electronic region, as well as due to presence of 3 lone pairs. So total 5 region of electron density, 5 regions of electron density. So it has a trigonal bipyramidal geometry. This is the electronic geometry. But this molecule has actual geometry, molecular geometry is a linear. This is very important, because 3 lone pairs of central iodine acquires the equatorial positions. So this molecule, this ion, I3 minus ion, has a molecular geometry linear, but electron geometry is a trigonal bipyramidal. Okay. Now with this explanation, you can determine the electron geometry as well as the molecular geometry of XeF2, xenon difluoride, for exercise. Okay. Thanks for watching this video.